Hello everybody, Namaskar. Now we are in the 14th lecture of the course, and today in the next half an hour we will study processing and preservation of fruits and vegetables by removal of heat. The major aspects of this lecture will be cooling and its types, refrigeration, then chilling and freezing technology, and finally, we will also discuss freeze drying and freeze concentration. In fact, the freeze drying and freeze concentration can be considered as a combination technology where we are lowering down the temperature as well as also we are removing the moisture. So, it is a combination of lowering the temperature and removal of the moisture, and which finally gives the beneficial effect on preservation and processing. So, let us see what is the cooling of fruits and vegetable. In earlier lecture also we have discussed a brief about the cooling process, particularly in relation to the temperature in relation to the transportation etc. But here we will discuss more about overall effect of the cooling process and cooling technology on the quality from the processing point of view, from the storage point of view and other aspects. Okay. So, cooling is the process of removal of heat from the fruits and vegetables and such other products to lower their temperature to ambient conditions or to storage conditions or other required treatments etc. It is also called as pre-cooling or removal of field heat by rapidly lowering the temperature of post-harvest produce to near storage temperature. So, the harvest for primary processing, that is the cooling, and it reduces the metabolic activity, it reduces growth of microorganism, it slows down the spoilage, and all these effects give the benefits like reducing the changes to the organoleptic and nutritional quality of the product. These are minimized, and also it helps in maintaining the product quality as well as product safety. This process is done before the produce is transported to market or also put into the cold storage. Okay. Different types of cooling include chilled air cooling, vacuum cooling, or chilled water or hydro cooling. Chilled air involves passing refrigerated air on the fruits or vegetables. The loss of moisture results in reduced weight and wilting sometimes. Vacuum involves placing the fruits or vegetable in a sealed chamber and reducing the pressure through the vacuum pump. It is suitable for leafy vegetables like lettuce, spinach etc. The chilled water cooling or hydro cooling involves spraying of chilled water on the produce by its direct immersion in the cold water. Either the chilled water can be sprayed on the produce or the produce can be directly immersed in the cold water. However, they do not lead to moisture loss during cooling, but there may be some contamination etc. if the water is not of good quality. Okay. So, disinfection is the major problem here, for which the recirculated water or the water which is used for chilled cooling or hydro cooling is chlorinated or it is sometimes sanitized. Okay. Chilled air cooling, you can see in the figure here that air exchange an exchange of heat is accomplished by changing the temperature of the air. Such temperature changes usually occur at constant pressure. The chilled air is passed inside the storage room or inside the package. There is a extraction fan which removes warm air from the cartons or storage environment. So, the amount of sensible heat change in the air may be estimated by Qs is equal to mCPA T2 minus T1, where m is the mass flow rate of the air, CPA is the specific heat of air, and T2 minus T1 is the temperature difference between the outgoing air and incoming air. Vacuum cooling, it is based on evaporation cooling. Okay, that is evaporation or boiling process requires energy, and this energy is taken from the product which cools down. You can see here in the figure schematic, there is a vacuum chamber, all right. It is attached with the cooling coil, condensates, that is the vaporized water to separate, that is the from the vacuum where the pressure is lower, then the water vapor comes, then this condenser, it condenses the water, condensed water is collected here, and this vacuum pump is used to provide that the reduce the pressure or create the vacuum inside the chamber. Okay. So, here one thing is important, that energy, obviously you know that it never lasts. So, in vacuum cooling energy is never lasts, only the thing is that the whatever energy is released, that is equal to energy taken, Q released is equal to Q taken. So, in evaporation cooling, the heat energy released from the object is taken by evaporating water. Okay. So, the Q released is equal to m food, that is mass of food, multiplied by Cp specific heat, or delta T, which is the temperature difference, or Q taken, it will be is equal to mass of water, m water, delta HV, where HV is the evaporation heat of water. So, that is the Q released is basically the whatever heat is released from the food, is that heat is taken by the water. Hydrocooling, it is that here a graph is indicated, that is by this graph, that is the decimal temperature difference, how it is related with the minutes of active cooling. So, time center that is the it is time center temperature response. So, from this graph, these lines which you are seeing, these are the various commodities, these lines are for various commodities, and once you find out, once you calculate the DTD, that is from this equation, like DTD is equal to TF minus TW divided by TI minus TW, where the TF is the target produced temperature, TI is the initial temperature of the product, and TW is the temperature of the chilled water. So, from this one can calculate DTD, and if you know the DTD, so from this line for the specific commodity, one can calculate, that is what should be the for particular DTD, what should be the expected time for cooling the produce. Okay. And that is the from this, you see on the x axis, it is the minutes of active cooling. So, one can calculate and do accordingly. Then now let us see refrigeration. Refrigeration or chilling is another technology. It is the under refrigerated conditions or less than 5 degrees Celsius, most of the pathogens their growth is stopped. A few pathogens, however, may grow slowly under these conditions. Okay. Pure water freezes at 0 degrees Celsius, but the food freezes at a temperature less than 0 degrees Celsius, and this is mainly because inside the food system there are various solutes are there, that solids etc. are dissolved in the food, which lower down its freezing point. No organism, whether pathogen or spoilage, grows below 0 degrees Celsius. Mostly, that is, I can say this is a very strong statement, but there might be some exceptions, but in as a general, as a rule of thumb, most of the pathogenic or spoilage microorganisms, their growth is stopped below 0 degrees. They do not normally grow at under freezing conditions. Refrigeration also slows down the spoilage microorganism growth and slows down the chemical reactions that can lead to off flavor. Okay. So, normally if you see in even in our household refrigerator, that is in the refrigerator, normally the temperature may be in the 0 to 8 degrees Celsius. Therefore, the storage under these conditions may be called as refrigerated storage, and the frozen storage, the temperature may vary from 0 to minus 23 degrees Celsius depending upon the commodity and its composition etc. So, every 10 degree lowering in the temperature makes the shelf life of the commodity almost double. So, for keeping that the material in the food for the required time, what should be, we normally that is we calculate the refrigeration load of the storage, refrigeration storage or cold storage can be calculated that is by considering different heats, that is there are 5 types of heats etc. That is the, and this refrigeration load is the amount of heat that is removed by the refrigeration system, and it is important attribute while designing the cold storage facility etc. One must calculate what should be the refrigeration load of the system. So, it includes like heat of respiration is there is total weight of the produce multiplied by heat of respiration of the produce, means that is whatever will be the heat of respiration. So, you have to find out that what is the total amount of the produce that you want to keep inside the storage. Then heat of respiration can be calculated, then heat removed from the container or from the commodity. So, that can be calculated by the number of containers containing the produce multiplied by container weight multiplied by Cp of the container multiplied by temperature difference, and then the whole thing divided by time required. Heat evolved by the operators and light, because some of the heats when operators go inside and then there may be some heat change evolve or even lights etc. If there are switch on, some heat may be there. So, that is also calculated. So, it is heat evolved by operator and light is equal to the heat produced by the operator and the bulbs per second. Then there may be some heat loss through the walls and roofs, and that can be calculated by thermal conductivity of the K is the insulation multiplied by area multiplied by temperature of the ambient air minus temperature of the chilled air, and whole thing divided by insulation thickness. So, that will give the total heat loss through the walls and roofs. And finally, the heat loss through the floor is calculated by K of the concrete multiplied by area multiplied by T soil minus T chiller divided by floor thickness. So, the total heat load of the capacity will be the sum of all these 5 loads. Okay. So, chilling, it is the that it is the removal of heat, that there are chilling or freezing processes. Temperature range in the chilling is about 1 to 8 degrees Celsius, and depending upon the type of fruits and vegetables. So, chilling is an important unit operation to extend the shelf life of fresh as well as processed fruits and vegetables. Even sensory and nutritional properties are minimally affected by chilling. It is convenient, easy to prepare, high quality and healthy products can be obtained by chilling technology, are natural and fresh for longer time. That is the maintaining the chilling storage and chilling requirement, even chill room etc. keeps the commodities in fresh form. So, to chill fresh foods, it is necessary to remove both sensible heat, also known as field heat, and heat generated by the respiratory activity. It is recommended temperature and relative humidity for fruits and vegetables with their storage life. We have discussed earlier in the lecture 8. So, those things apply here as well. The production of respiratory heat at 20 degrees Celsius and atmospheric pressure is given by this equation. You can see that 1 mole of glucose plus 6 moles of oxygen, it produces 6 moles of carbon dioxide plus 6 H2O up as this much 2.835 into 10 to the power 3 kilojoule per kilomole glucose is this much heat is produced. So, the in this table I have given the rates of heat evolved in watt per ton from the fruits and vegetables stored at different temperatures. For example, apples, when they are stored at 0 degrees Celsius, they may produce 10 to 15 watt per ton of the heat, whereas the same apple at 15 degrees Celsius it may produce 41 to 92 watts per ton. Grapes produces 4 to 7 watts per ton at 0 degrees Celsius, 9 to 17 watts per ton at 5 degrees Celsius, or 30 to 35 watts per ton at 15 degrees Celsius. So, these are the important commodities. So, that is at what rate they evolve the heat, that is at different temperature is shown, that this gives important, this can be used for calculation of the refrigeration load etc. So, cooling rate and duration, that is cooling rate may be defined as the dt by dt, that is Cr is equal to dt by dt, where d capital T is the temperature difference and dt small t is the time difference. So, in this calculation several assumptions are considered to obtain the time temperature function, like the product is homogeneous, if it is kept in homogeneously filled, temperature is same at every point inside the mass, inside the room, temperature of the cooling medium is constant, there is no mass transfer between the product and the medium, and sensitive heat removed from the product equals to the convective heat transfer from the product to the medium. So, based on these assumptions, the equation is 1 m c dt is equal to minus s h t minus t 0 dt. So, capital T, that is the temperature, is T 0 plus T I minus T 0 exponential minus H s by m c t, or small t, that is the time, is equal to m c minus H s ln T I minus T 0 divided by T f minus T 0. So, m and c are the mass and specific heat of the fruit or the vegetable, h is the convective heat transfer coefficient, s is the surface area, T I and T I are the initial and final temperatures of the product, and T 0 is the cooling medium temperature. So, from these equations one can calculate cooling rate and the duration of the cooling. Then the chilling injury, it is an important aspect which is associated with the chilling of the fruits. We also briefly discussed this in earlier lecture. So, the fruits and vegetables particularly which are grown in the tropical and subtropical regions suffer from chilling injury, and that is due to cold storage, chilling storage. So, the cold sensitive temperature of subtropical fruit is generally 5 to 8 degrees Celsius, and while to that of the tropical fruit it may be less than 12 degrees Celsius. So, chilling injury is different from the freezing damage, in that it refers to the physiological damage of the susceptible part organs, the organs which are susceptible to the cold, because of this is mainly because of the exposure to temperature above the freezing point. Chilling injury in most fruit is not easy to detect during storage environment. It is the symptom will only appear, it will be visible only after the commodity has been taken out of the cold room. So, the mechanism that is the which are proposed for the chilling injury, biochemical mechanism, that is there is a cell membrane damage hypothesis or reactive oxygen stress ROS hypothesis, and these both of these hypotheses, that is they destroy the membrane functions causing physiological or metabolic disorder in the commodity, and which ultimately is manifested into different types of injury. So, there are different types of chilling injury in fruits and vegetables, maybe surface water stains, which is generally evident in cucumber, kiwi fruit, etc. You can see here in the picture, or it may be that surface depression and browning. In the case of banana, oranges, green apple, this type of chilling injury is more common. You can see some of the picture, that is where the chilling injury in banana after 2 weeks of storage at different temperatures, it is shown. Then in the woolly texture in peach and nectarine, you can see here chilling injury in peach and evolution over the time is shown in the figure. Then other type of chilling injury is the loss of ability to mature, that is in the case of tomato and guava, this type of injury is seen. Okay, when the cold in the cold room temperature is not maintained to the proper required recommended conditions. Okay. Then this seed and calyx browning, that is which is more common in the sweet potato, that is you can see here, or in the sweet pepper chilling injury in the bell pepper is shown here in the figure, that is after 25 days or after 28 days the storage, cold storage. Okay. Then there are methods to control the chilling injury, okay, like physical methods like low temperature conditioning, heat treatment, storage near freezing temperature, UV radiation, CA, storage and edible coatings, etc. Chemical method like ethylene dip, oxalic acid, calcium ion, GABA, etc. can be used, or biotechnological approach, that is transgenic technology, which enhances the resistance through gene based on regulatory microRNA. So, either of these approaches can be used. Now, we will switch over to freezing. That is, freezing is an unit operation that is intended to preserve food without causing significant changes to their sensory qualities or nutritional value. Okay. So, the freezing involves reduction in temperature of a food below its freezing point, and generally that is it may be temperature may be minus 18 degrees Celsius or below that, depending upon the type of the food and its composition, what are the various constituents present in it. So, water in the food undergoes state change to form ice crystals. So, the immobilization of water as ice and the resulting concentration of dissolved solutes in the unfrozen water lowers the water activity and which extends the shelf life of the food. This microbial deterioration is eliminated. It reduces rate of enzyme and calcium reaction, that is chemical reactions, efficient handling and transportation of the, it extends the shelf life, and it is convenient to use technology, the freezing. Okay. So, here you see the freezing process. Okay. That these are two curves is shown, one is the freezing curve of the pure water and other is the freezing curve of freezing process of the food. Okay. The pure water you can say it is at 0 degree, it is frozen temperature, the water will come like this, and then the crystallization will start, it will come to like that product range. Whereas in the food there is a super cooling. Okay. You can see there is a, and then phase change and the temperature increases, come to the freezing point and then it reduces. So, there are several methods of freezing based on which the quality of the finally frozen product may vary. According to the International Institute of Refrigeration, freezing is divided into 3 stages: pre-freezing, that is the freezing until the appearance of the first crystal; then freezing, it is where the phase change takes place, that is the phase change, water is converted into ice, and then reduction to the storage temperature, third phase. The last stage starts when the product temperature reaches to the point where most freezable water has been converted into ice, and it ends when the temperature is reduced to the storage temperature. So, the quality of the frozen product is mostly affected by the rate of freezing, while the time of freezing is calculated according to the rate of freezing. So, this is in this graph I have explained all the stages of the freezing curve, like in the figure if you see that A to S, it is the removal of sensible heat, no water ice transformation takes place in this region. Then comes S, as I told you, it is the supercooling where the water remains liquid below the freezing point. Then after that the temperature increases little bit, it comes to the B, freezing SB, temperature rises as the ice crystal forms and releases the heat of latent heat of crystallization. Okay. Then it comes B is the initial freezing point, it is a function of number of dissolved particles present in the solution. So, initial freezing point, the crystallization occurs at point B. Then B to C, this is the phase change, water is crystallized, latent heat of crystallization is removed, but due to increase in the solute concentration, freezing point also decreases, that is it comes. Then C, it comes to C, and then from C to D, solute becomes supersaturated and crystallizes out. Lambda is again released and the temperature rises to eutectic temperature, okay, of that for that solute. So, D. Then D to E, crystallization of water and solute continues. The temperature of the ice water mixture falls to the temperature of the freezer. Then E to F finally, E to F, this is the point, then their ice formation and solute concentration continues until no more water can be frozen. Means when F is the point where all the water is freezable, water is frozen, there is no water remaining which can be frozen. Finally, F is the temperature at F is known as glass transition. temperature of amorphous concentrated solution. Here unfrozen liquid is converted from viscoelastic to brittle, amorphous or solid glass. Okay. So, slow freezing versus fast freezing is again, that is the, you can see here in the freezing, that is the freezing rate. These two lying, that is time taken for a temperature to pass through critical zone is known as freezing rate. So, generally you can take these two lines, that is the slow freezing line and fast freezing line, okay, and this is the critical zones. Okay. So, the slow freezing generally it has 1 to 10 degree Celsius per hour rate, commercial freezing have 10 to 50 degree Celsius per hour, and fast freezing has more than 100 degree Celsius. So, in the slow freezing mostly, that is there is a small number of ice crystals forms and of larger size. You can see here in the picture, that is the solute concentrates here. So, there may be dislocation of because this large size of the ice crystal there may be. So, finally, after thawing there may be certain structural dislocation etc. of the commodity, whereas in the fast freezing from quality point of view it is good. There are large number of ice crystals of smaller size. So, there is no structural or cellular dislocation etc. as you can see here inside the cytoplasm also the small crystals are formed and they are uniform, the structure remains intact, there is no damage etc. So, structural change is minimum in the case of fast freezing. So, this Planck's equation can be used to calculate the freezing time, like here Tf is equal to rho f lambda f minus Tf by Ta divided by Pa by H plus Ra square by K. And in this equations various assumptions are that heat transfer is one dimensional, initial temperature of the food is unknown, freezing air temperature is constant, latent heat of fusion is removed at a constant temperature, and the properties of foods are constant above the and below the freezing point, but they are different, and heat transfer within the food is by conduction only. Okay. So, and this P and R which are constants, they depends upon the geometry of the material which is being frozen, like it is infinite slab, P is 1 by 2 and R is 1 by 8. For infinite cylinder it is 1 by R and 1 by 16. For sphere it is P is 1 by 6 and R is 1 by 24. All these crystals like LF is the change of the latent heat of the product, Tf is the freezing temperature, Ta is the freezing air temperature etc. Okay. A is the thickness or diameter of the object and K is the thermal conductivity of the frozen material etc. So, using this Planck equation one can calculate the freezing time. Okay. Now, after freezing another important aspect is thawing, because before consuming the product, once it is taken out of frozen environment, it has to be brought to the normal level, original level. So, that is freezing, thawing is you can say is the reverse of the freezing. When the frozen food is thawed using air or water, the surface ice melts from a layer of the water, and thawing is a longer process, it is a comparatively slow process than the freezing, because over the progress of the freezing time the heat transfer medium becomes water, and water transfer the heat or conduct the heat at a lower rate than that of the ice. So, that is why you can see here in the figure it is the thawing and this is the freezing line. So, slow freezing line and it is thawing line. Okay. So, due to lower thermal conductivity as I told you and thermal diffusivity of water than ice, the surface layer of water reduces the rate at which heat is conducted to be frozen interior. This increases as the thawing progresses. So, in the thawing curve A to B is due to the absence of a significant layer of water around the food, and B to C it is when the temperature of the food is near to that melting ice. So, drip loss occurs due to damage in cellular structure by slow freezing. Okay. Thawing time can be calculated using this equation. Okay. And here that is this T is equal to dC by EFH delta S10 minus divided by Ta minus Tf or P1 plus P2 Bi, and then this P1 and P2 calculated is this equation where the St is the Stiffes number and Bi and pk are the Boyett number and Planck's number. So, using this equation, Boyett number and Planck number and Stephen constant or Stephen number can be calculated, and this can be used finally to find out the time. Okay. This is that is dc is the characteristic dimension, ef is the shape factor, h is the convective heat transfer coefficient, delta H10 is the volumetric enthalpy, that is change of product from 0 to 10 degree, Ta and Tf are the medium and freezing temperature, and P1 and P2 are constant. So, these things, these parameters are used to calculate the thawing times using the equation which I have given here. Okay. Then finally, we will come to the freeze drying, that is it is also termed as lyophilization. It is a drying process. As I told you, it is a combination of drying, removal of water and removal of heat. That is the drying process where the wet product is first frozen to a solid phase, and subsequently the product is dried by direct sublimation of the ice under the reduced pressure. So, you can say that typically it is done to a final moisture content of 1 to 3%, that is it can be removed. So, freezing of the product is dried by direct sublimation under the pressure. Okay, it is a schematic, that is the ice converted into water is converted into ice, and ice is directly sublime into vapor form. Here the sublimation process is explained here. You can see this is the phase diagram of water. So, there exists a triple point A. So, below this at this particular pressure and temperature, which is normally 611.73 Pascal pressure and 0.01 degree Celsius temperature, that is the triple point. So, one has to maintain the temperature and pressure below that is the triple point temperature and pressure, and then only the directly solid will be sublime to gas. Otherwise, it will go melting. If the temperature and pressure is above that, then it may go the normal process that solid may melt and then liquid may evaporate. So, in order to conduct directly the sublimation, it has to be maintained in the system, that the temperature and pressure is to be maintained below the critical triple point temperature. So, drying takes in two steps, that is the primary drying and secondary drying. The primary drying step involves sublimation of ice under vacuum, whereas the secondary drying steps begins when there is no ice from unbound water is in the product, and then moisture comes from partially bound water in the dried material. Okay. In the drying, heat and mass transfer can be continuous. It is also freeze drying is a continuous heat and mass transfer operation. You can see here it is a frozen material where there is a frozen product ice etc. there, dry layer. From the heat source you are producing the heat, and this heat is causing the direct evaporation of water, that is the sublimation of the ice into vapor form. So, in the condenser where it is condensed and it is used in the water. So, the rate of sublimation is given by G is equal to A Pi minus Pc divided by Rd plus Rs plus K1 inverse. Okay. G is the rate of sublimation, A is the sublimation area, Pi is the vapor pressure of ice, Pc is the condenser vapor pressure, Rd, Rs are the resistance to the dry layer in the food as well as resistance in the space between the food and the condenser, this space, and K1 is the constant depending upon the molecular weight of the subliming surface. Okay. So, the heat of sublimation delta Hs must be supplied, and therefore, G is equal to Q by delta Hs, where Q is the heat flux. So, this equation one can find out the rate of sublimation. Then heat transfer in the freeze drying, if you see, it is a instant between the interface between the frozen zone and the dry zone is called as sublimation front. So, heat transfer to the sublimation front is through the frozen layer. The rate of heat transfer depends on the thickness and thermal conductivity of the figure. You can see here in the figure, there is mass transfer, heat transfer, both are shown. This is the frozen layer, these are the dashed line, frozen layer, other are dry layers. Okay. So, there may be heat transfer through the frozen layer or heat transfer through the dried layer. So, in the case this case when the heat transfer is to the dry layer, the rate of heat transfer to the sublimation plant depends on the thickness of the area of the food, the thermal conductivity of the dry layer, and the temperature difference between the surface of the food and the ice front. In the third case, there may be heating by microwaves, that is internal heat generation. Okay, heat is generated at the ice front internally, and the rate of heat transfer is not influenced by the thermal conductivity of ice or of the dry food or the thickness of the dry layer, etc., because here the heat is internally generated. Okay. So, mass transfer rate in the freeze drying is affected by pressure in the drying chamber, okay, temperature of the vapor condenser, and this temperature of the ice at the sublimation front. Drying time can be calculated using this equation: Td is equal to L square rho m0 minus mf whole thing multiplied by delta Hs divided by 8k Ts minus Ti. So, from this equation you can conclude that the total drying time Td depends upon the maximum permissible surface temperature Ts, temperature of the sublimation front Ti, initial and final moisture content M0 and Mf, bulk density of the solid, that is rho, latent heat of sublimation delta Hs, thickness of the slab L, and thermal conductivity of the dry layer. So, from this one can calculate the freeze drying time. Okay. Then finally, freeze concentration. It is another process. In the drying, you are freeze drying the ice which is formed by freezing process, that is sublimed. But in the freeze concentration process, this is a important method, that is it involves the fractional crystallization of water to ice and subsequent removal of the ice. Okay. And this is achieved normally by in a pedal crystallizer, and it is potentially attractive method for concentration of fruit juices, coffee, tea, and selected alcoholic beverages, etc., and particularly for preparation of high quality juice, fruit juice concentrate, etc., before making instant tea or instant coffee. Their coffee brew or tea brew are normally freeze concentrated and then they are spray dried. Okay. So, this system involves that, as I told you, crystal nucleation, then crystal growth. So, the standard freezing process, the freezing is done, but all water is not frozen, that partially, and then this ice which is formed, it is crushed. So, either by centrifugation or by other separation processes, ice is separated from the crystal. So, you get that is a concentrated solution, that is some amount, a partial amount water is removed in the form of ice. So, centrifugation or the separation. So, finally, now we summarize this lecture by saying that refrigeration is used to stop the growth of bacteria, not to kill them. These cooling technologies, yes, one thing is important, that they will just suppress the growth. It is not a killing or inhibiting technology. So, cooling or chilling or other process, that is maybe a standard process may be used. Cooling can be done in 3 ways, like air cooling, vacuum cooling, hydro cooling. Removal of heat is generally done in either in the chilling process or by the freezing. Chilling requires temperature of -1 to 8 degrees Celsius, whereas freezing requires -18 degree or even lower than that. Fast freezing produces small but more nuclei, more ice crystals, which is better than the slow freezing, where large but less number of ice crystal nuclei are formed. Freeze drying is an important technique to dehydrate the food product with minimal reduction in the nutritional properties. In fact, freezing and freeze drying are considered to be the best processes as far as the quality of the end product produced is concerned. However, this may be little bit costlier process, particularly freeze drying. It may be costly process, but the quality advantages are much higher here. So, these are the references which has been used in this lecture, and finally, thank you all for your patience hearing.